Hi everyone, my name is Zsolt Szabó and I'm going to talk about quantum error correction. Let me note that I'm not an expert of this topic. I spent the last couple of days reading what I could find useful, and this is my understanding of it. First, I'm going to talk about classical error correction to get you familiar with some notions that have very beautiful analogues in quantum error correction. So let's get started. This is the diagram of a general communication system. There is a source that produces some message. This message is encoded into a signal, and the signal is sent through a channel. On the other end, the received signal is decoded into the received message, and this reaches some destination. The channel may signify spatial transmission, but it can also signify storage for later retrieval. The encoder is concerned with data compression, with data encryption, and with error correction encoding. The decoder basically undoes what the encoder did. It decompresses, decrypts, and decodes the received signal. Error correction is needed to protect the signal from the noise of the channel. Let's see the basic idea of error correction. Suppose there is a signal space S, and the error is treated as a distance d on S. A basic assumption is that the received signal V is not very far from the original signal U. So a good strategy is to limit the inputs of the noisy channel. This defines the code C, and to spread the code words apart from each other as much as possible. When the signal V is received, the best estimate for the input of the noisy channel is the code word C' that is closest to V. The most important parameter of the code is the code distance, that is the minimum distance between the code words. An error is correctable if it's less than half of the code distance, and it is detectable if it's less than the code distance. So let's see the big picture. Suppose there is a message space M, and this is mapped injectively onto the code by the generator map G. A message M is encoded into a logical message ML, and this is sent through the noisy channel. Now, for the sake of illustration, let's assume that the received signal V is closest to this code word here. Now, the decoder falsely assumes that the input of the noisy channel was this code word ML' and decodes it to the wrong message M'. Regardless of the quality of this method, finding the code word that is closest to the received signal V is a problem, and this is the motivation for linear codes. In case of linear codes, the message space M and the signal space S are linear spaces over the same field. And the code is a subspace of S, and it is the range of the generator map G, which is a linear map between M and S. Since G is injective, the code is isomorphic to the message space M. Note that this figure only shows the linear character of the code correctly. Naturally, the code words are not as bunched up as shown by the figure. The cosets of the code are called error cosets. These, on the one hand, partition the signal space S, and on the other hand, form a vector space, which I will call vector space of error cosets. There is also a parity map H, that is a linear map between S and the vector space of error cosets, and it maps a received signal V to the error coset that contains V. It follows that C is a kernel of H. The code word closest to the received signal V is obtained by subtracting from V a vector E. This vector E is called the error vector of the error coset, and by definition is the vector in the error coset that is closest to the zero vector. Since the code is a linear subspace, the zero vector has to be a code word. Again, this method is based on the assumption that the noise does not alter the signal too much. The advantage is that E does not depend on the received signal V. It depends only on the error coset, so it can be calculated in advance. The error coset that contains the received signal V still remains to be found. I will show how this is done for binary linear codes. Now the message space M and the signal space S is some power of GF2. Let this power be K and N. Then the vector space of error cosets is isomorphic to GF2 to the n minus k. The distance is the Hamming distance, which is the number of positions where the two binary sequences differ. The parameters of a binary linear code are the number of bits in code words, n, the number of encoded bits, k, and the code distance. M and S have canonical bases. And let's assume that the basis is fixed also in the vector space of error cosets. Then the generator map has an n by k generator matrix G, and the parity map has an n minus k by n parity matrix H. The parity matrix maps the received signal V onto a vector of GF2 to the n minus k. This vector is called the syndrome, and it is usually denoted by S. Let's see an example, the Hamming code with parameter 743. The generator matrix can be split into two blocks. One of them is the 4x4 identity matrix, and the other one is a matrix A. It follows that the logical message ML contains a copy of the original message M and some redundancy bits. Codes that have this property are called block codes, so the Hamming code is a block code. The parity matrix can also be split into two blocks, and the first one is the same matrix A, and the second one is the 3x3 identity matrix. Suppose we have a message 0110, and the corresponding logical message is 0110110. The syndrome is 0 since the logical message is a code word. Now let me do a bit flip in the third bit. Now we have a non-zero syndrome. This syndrome 011 is associated in advance with the error vector 0010000. So this bit flip error can be corrected. The relation between the various syndromes and error patterns usually is not trivial, but as I said earlier, it can be calculated in advance. Now let's see the quantum version of the error correction. The analog of the message space M is a message Hilbert space HM, and to each message there corresponds a message state, and these message states form an orthonormal basis for HM. This relation is very much the same as the one between a bit and a qubit. To each classical state of a bit there corresponds a basis state, and these basis states form an orthonormal basis in the Hilbert space of the qubit. This orthonormal basis is called the computational basis. In order to construct an error correcting code, we need redundancy. The redundancy now is represented by this vector R, which lives in the Hilbert space of the redundancies HR. The quantum analog of the signal space S is the tensor product of HM and HR. Now recall that in the classical case, the generator map G was defined on the message space M, and it mapped messages to logical messages. The set of logical messages was the code C, a subspace of the signal space S. In contrast, in the quantum case, the generator map is a unitary operator G, and this acts on the tensor product space HM times HR. Being a unitary operator, G is subject to the no-cloning theorem, which basically states that redundancies cannot be added naively as it was done in the classical case. Now let's see how to overcome this problem. Consider the product states that arise as the tensor product of a message state and the redundancy state. Their image under G are the logical message states, and these by definition span the code space HC. The quantum analog of the parity map is a projective measurement described by the parity operator H. The eigenvalues of H are the syndromes, and one of its eigen subspaces is the code space. At the beginning of the communication process, we have a message register that is in the state psi. This state psi we want to send through the communication system, a part of which is the noisy channel. There is also a redundancy register that is in the state R. The tensor product of psi and R is encoded into a logical state psi L, and this psi L is sent through the noisy channel and is altered by the noise. Suppose that the error produced by the noise is coherent, which means that it can be described by a unitary operator E. E maps the logical state psi L onto a vector phi that may have components in each of the eigen subspaces of the parity operator H. The parity is measured using a pointer whose Hilbert space is HP. This Hilbert space is spanned by the basis states S0, S1, S2, etc. and these correspond to the pointer indicating the respective syndrome. In the beginning, the pointer is in the state S0 and then it is coupled to the register to be measured, which is in the state phi. The coupling is described by this operator A, whose expression basically says that the pointer is moved by the eigenstates of the parity operator H. The result of the coupling is an entangled state of the composite system that consists of the pointer and the register to be measured. The next step is a projective measurement on the pointer. Then the entangled state of the composite system collapses into a product state, in which the pointer indicates syndrome Si, and the state of the register is entirely in the eigensubspace of the parity operator H corresponding to that syndrome. This disturbance by the measurement is also part of the quantum error correction process. Now that the syndrome is known, an appropriate recovery operator can be chosen to restore the state of the register to the code space. The result is the received logical state psi L prime. Psi L prime is then decoded into the tensor product of the received message state psi prime and the redundancy state. The state psi prime corresponds to the classical received message M prime. To show an example, I will examine the detection code with parameters 422. In analogy with the classical case, the first parameter is the number of qubits in the logical states. The second one is the number of encoded qubits, and the third one is the code distance. These parameters are defined in the so-called stabilizer formalism. In what follows, I will only scratch the surface of this formalism. In the case of the 422 detection code, the message Hilbert space HM is the Hilbert space of 2 qubits, and so is the redundancy Hilbert space HR. Here are the product states that are the tensor product of a message state and the redundancy state, and here are the logical message states. I will not go into the details because this code is best described in terms of its stabilizers. Now this means the following. The parity operator H has two components, H1 and H2. And the first one is the fourfold Kronecker product of the Pauli matrix X. And the second one is the fourfold Kronecker product of the Pauli matrix Z. These matrices are assumed to be in the computational basis, and the lower index shows on which qubit the respective matrix acts. The two components of the parity operator commute, and any logical state from the code space is a joint eigenstate. The corresponding eigenvalues are +1, +1. This situation is described by saying that the two components stabilize the code space. Before going into the details of error correction, let's see what can we say about the errors themselves. Any coherent error can be expanded into a linear combination of the four Pauli matrices. Now, since the Pauli matrices are unitary, they also represent errors. For example, X is called the bit flip error because it exchanges the two computational basis states, and Z is called the phase flip error because it reverses the phase of the second basis state. Now suppose that the ith qubit suffers a coherent error described by the matrix EI. The action of EI on a logical state psi L, denoted by phi, can also be expanded into a linear combination, and the vectors that appear in this linear combination are joint eigenstates of the two components of the parity operator. When the parity is measured, psi collapses into one of these vectors, and as I said earlier, this is also part of the error correction process. The syndrome +1 shows that there was no error, so no further action is needed. +1 shows that there was a bit flip, -1 shows that there was a phase flip, and -1 shows that there was both a bit flip and a phase flip. The syndrome is independent of the index of the qubit, so it does not show which qubit suffered from the noise. Therefore, this code can only detect the error, but it cannot correct it. Now assume that there was a bit flip in 2 qubits. This error does not take out from the code space, so a measurement of the parity falsely shows that there was no error. This illustrates that the 422 detection code cannot even detect 2-qubit errors. I think I will stop here. Thank you for your attention. See the references in the description of the video and see you soon. Bye bye.